I recently graduated from CMU and then done assignments. Today I'm going to talk about finding best LP relaxations for directed curve problems. So everything I'm going to say, every new result that I'm going to say in this talk will be based on some papers either published this year or submitted this year or written this year. So it's interesting to see how many people and how many papers are involved here. So for example, Chandra and Vivek had a really nice paper introducing the problem of a multicut H, which is a special case of a multicut when the demand graph is fixed to be H. Okay? And then around the same time, I independently had some results about multicut interdiction firefighter problems. And then based on these techniques and with other algorithmic ideas, we also looked at global cut problems that I'm going to introduce later. And then my co-authors also worked on a very cool problem called linear 3-cut problem, which is a special case of a multicut H. And then they proved the optimal approximation algorithm whose approximation ratio is a square root of 2. And then finally, I was talking to Vivek again, and then we came up with an optimal LP for multicut H for every demand graph H. And then this will be the core of this talk. Okay. So let me start. So our focus will be a directed multicut problem. It's a very classical problem. So in this problem, the input is very simple. We're going to get directed graph G, and then K pairs S1, T1 through SK, TK. Okay. So in this example, and that goal is to remove the minimum edges to make sure that in the supply graph, there's no path from Si to Ti for every I. Okay. So in this example, if you remove these two edges, then we can see that there's no path from S1 to T1, and there's no path from S2 to T2. Okay? So these two edges form a valid solution for directed multicut. And I'm sure that they're going to be the optimal solution. Okay, so this is a very classical problem. And then it's been studied a lot previously. So if you want to write the approximation algorithm in terms of n, then we already knew root n approximation algorithm, which was finally improved to n to the 11 over 23 due to Agarwal, Alon, and Charikar. And even from the lower bound side, by the nice work of Juzo and Kana, we know that full cut LP has a gap of at least n to the 1 over 7. And then this problem is also NP hard to approximate within an almost polynomial factor. Okay? So there's a very interesting gap between 1 over 7 and 11 over 23 in the exponent. But we understand this problem pretty well. Okay? But if you want to express the approximation ratio in terms of k, and let's suppose that k is some constant, then we know that there's a very easy k approximation algorithm. Just compute the minimum Si, Ti cut and take the union. But we know that we can't improve upon this easy k approximation algorithm using just standard flow cut LP. Okay? When k is less than log n, we know that flow cut gap is close to k, so we can't improve k approximation algorithm. And what Chandra and Vivek proved last year is that even when k is 2, they proved that it's unique games hard to approximate this problem within a factor of 1.5. Okay? So from now on, every hardness result I'm going to present is based on unique games. I feel bad to present unique games hardness after hearing that unique games is easy in almost every possible setting, but that's what I have. So they show this, and then as far as I knew, so 1.5 was the best hardness constant for as long as k is constant. So obviously the hardness result required that k should be growing with n. I think this is almost polynomial. And then for any constant k, 1.5 was the best hardness ratio we could. Okay, so what happened in 2017 is that Chandra and Vivek and I independently proved that directed multicut with k pairs is a unique games hard to approximate within a factor of k. So the trivial k approximation algorithm is optimal. So if I say something about these two proofs, so Vivek and Chandra's proof is a reduction from mean CSP that was studied by Ene, Bondrag, and Wu. And then they revealed the very interesting connections between different LP relaxations. So if you think about the cut problems, then the first standard LP you will think of is a flow cut LP. But if you think about CSP, then the first LP you will think of is a labeling LP that gives us some probability to some event that some variable gets some value. Okay? So those are like very different LPs, but they establish the connections between these two LP relaxations. So whereas my proof is based on like more or less direct reduction from unique games. So I didn't have these cool facts about LPs, but at least for me, my proof was conceptually simpler and then easier to adapt to other curve problems. So, but what Chandra and Vivek did that I didn't do is to introduce this very cool problem of multicut H. So let H be a fixed demand graph. Say that it's a constant size. So given this H, multicut H is a special case of a directed multicut problem. So now demand graph is fixed. So input is just supply graph, G, and the injective map pi from the vertices of H to vertices of G. So pi essentially specifies where the terminals are. And then given this input, our goal is to remove the minimum edges from G such that for every edge UV of H, we want to make sure that in supply graph, there's no path from the image of U to image of V in G. Okay. So if H looks like this, just like single edge, and G looks like this, then we can easily see that this problem is exactly min SDK problem that we can solve efficiently. But we can look at other H. So if H looks like this, then if H is this complete graph, complete directed acyclic graph, and then this problem is known as a linear K-cut when K is a number of vertices. And then this problem was also independently studied. So if you look at multicut H in general, then we know that it's going to have an easy EH approximation algorithm where EH denotes the number of edges of H. And then the previous hardness results show that it's going to be tight when H has K disjoint edges. But for some H, we know that we can do much better than this. So for example, if H is a complete bidirected graph, then this problem is exactly directed multi-way cut, and then we know two approximation for every H. Okay. And if H is a complete directed acyclic graph, then this problem, as I described earlier, it's called K linear cut. And then it has a log K approximation algorithm. And then surprisingly, its a flow cut gap is still open. So it's still possible that it admits a constant approximation algorithm where the constant doesn't depend on K at all. And then, as I said, my co-authors looked at this 3 linear cut problem, and then they got optimal root approximation algorithm due to matching the flow cut gap. Okay, so for some H, we can do much better. And then, interestingly, all these algorithms use a standard flow cut LP. Okay, so the natural question is for some fixed H. So can you come up with a better relaxation by adding many constraints so that we can improve slightly upon the standard LP? Okay, that was a question. But surprisingly, Chandra and Vivek proved that when H is a directed bipartite, so by directed bipartite, I mean the graph like this. So undirected version is bipartite, and then every edge is heading to the one direction. So they proved that when H is a directed bipartite, then multicut H is a unique Ames hard to approximate better than the worst flow cut gap. Okay, so if H looks like this, then actually the flow cut LP is the best LP you can write for. Okay, so then next natural question is what about general H? So unfortunately, I couldn't solve this problem. So it's still possible that flow cut gap is the best. But what we proved instead is that we came up with another LP relaxation, or I prefer to present it as an estimation algorithm that always outputs the lower bound of the optimal and hopefully very close, such that its unique Ames hard to do better than this LP relaxation or estimation algorithm. Okay. And then I want to introduce this LP relaxation. Okay. So before going this, let's briefly look at some of the hardness proof of the theorem by Chandra and Vivek, and I'm going to present the alternate proof based on my previous paper. So let's first look at what flow cut LP is. Okay. So the first thing I'll do is that I will consider vertex deletion version instead of edge deletion version, but we know that they're equivalent by taking the line graph. So everything is the same. The only restriction is that we cannot delete terminals, which is completely natural. And let's say T is a set of terminals. Okay. So this is LP. We wanted to minimize the summation of XV, where V is summed over the set of non-terminal vertices, such that for each path from the image of U to image of V, for every UV in the demand graph, we want that the summation of XV is at least 1. So this is like very standard constraint, and then X must be non-negative. Okay, that's it. So that's a pretty standard LP. But as I described earlier, it's going to have a gap. Okay. So suppose that H looks like this. H has 2 disjoint edges, and then G looks like this. Then you can easily see that opt is at least 2, because of deleting just one vertex will not do the job. If you just delete just one vertex, then either S1 can reach T1 or S2 can reach T2. But you can also notice that every S1 T1 path or every S2 T2 path must involve at least 3 internal vertices. So which means that if I give 1/3 to every non-terminal vertex, then it's going to be feasible for this LP. So the LP value is at most 4/3. So there's a gap of 1.5. So I also should mention that for this demand graph, if H is a 2 disjoint edges, the optimal LP gap will be approaching to 2, but I'm just using this 1.5 for simplicity. Okay, so given this LP, so let's try to prove hardness. So the first thing I'll do is I'll decide something called Dictator Test. For me, it's just another instance of multicut H. And so the first transformation I'll do is I'll replace every internal vertex by something called hypercube, L to the R. So this is a given instance. And then I'm going to replace every non-terminal vertex by a hypercube, like this. So here, L is 3 and R is 2. But they're just numbers. They don't matter too much here. So, and then I'm going to put edges. So I'm not going to show details, but the only thing I'm going to say is that if UV was an edge of the supply graph in the gap instance, then we're going to create some edges between corresponding hypercube appropriately. Okay, so this is all I'm going to say about Dictator Test. And then, so once we have some Dictator Test with some desired properties, then what we will eventually do is we wanted to prove unique games hardness. So we want to reduce from unique games. So, so as you saw, instance of unique games has just like one graph, and then each edge is some constraint. And then the goal is to give a label to each vertex to maximize the number of satisfied edges. Okay. So suppose that this graph with 2 vertices and 1 edge is our very hard unique games instance. And then so to prove that, to reduce this instance to multicut instance, so what I'm going to do is I'm going to replace each unique games vertex by this gigantic Dictator Test I constructed earlier. And then you see some problems because we have multiple copies of the same terminal, which we are not allowed to. So I'm going to just combine these terminals. And then I'm going to replace this blue unique games edge by multiple edges between the Dictator Test, again, appropriately. So I'm not going to show details. And then in the yes case, if unique games has a good labeling, then I'm going to prove that I just proved that there's some canonical solution slicing one slice from each hypercube that's going to be good for, that's going to be cheap and will do the job. But it's not going to work if unique games is not good. And then essentially, if unique games instance is not good, then the only thing we could do is entirely remove one hypercube or not. So we are going back to the analyzing integral solution of the gap instance. And then that's where the gap comes from. Okay? So I didn't show anything, but this is like very high level idea of how the hardness works. Okay? So yeah, suppose that we proved the directed bipartite case in this manner. Okay, so what is wrong with general H? Okay, so for general H, this is not general H. This is still directed bipartite. But one crucial trick I used for directed bipartite case is that for directed bipartite case, we know that in H, every vertex is a source or sink. Okay. And then if we have this, and actually then for every gap instance, we can also assume that every terminal is a source or sink. So we can easily convince ourselves this. And then this was kind of crucial in my reduction. Okay. Suppose that we have general H, even though this is not general H. But suppose that we have these bidirected edges between one terminal and then one non-terminal vertex. Then actually, but in the eyes of LP, I didn't change the instance at all. So the same LP solution will work. So, but somehow my reduction doesn't work at all. Okay? So main reason is because my reduction was stupid. But actually, the main reason my reduction was stupid is that, if you look at the LP solution, then the distance between S1 and T1 is 1, as required. That's what is required for LP. But the distance between S1 and S2 is only 2/3, which is strictly less than 1. And then distance between S2 and T1 is also strictly less than 1. Okay? So in some part of the proof, I wanted to prove that S1, T1 is disconnected if we remove some canonical solutions. But what someone can do is someone can start from S1 and then go to S2. It was possible because S1, S2 LP distance was less than 1. And then because S2 is a single vertex, you can refresh everything. You can do as if you started from S2, and then you can reach T1. Okay, so this is like very high level idea, but somehow, so this fact was troublesome for me. So I was really very disappointed for a while, but actually I realized one trivial observation. such that in order to cut S1 from T1, we need to cut either S1 from S2 or S2 from T1. Okay? So this failure in proving hardness somehow inspired me to go to the algorithm. So sorry for this hand-wavy hardness. Let's go to crisp algorithm. So here's the algorithm. So algorithm fits in this box. So it's very simple. So let's say that directed graph F is unambiguous if for every edge UV of this graph and every third vertex W, either UW is an edge or WV is an edge. Okay? So if you interpret F as a demand graph, which we will, it means that if you want to cut UV, then you need to cut either UW or WV, which is very natural. Okay? So, and then it's equivalent to saying that the directed complement of F is a transitive graph. Okay, so given this definition, here's the algorithm. Okay, so I'm going to describe it as an estimation algorithm for this problem, which will output single value, which is always the lower bound of the opt. So given a supply graph G, we're going to try every possible unambiguous F on the same set of vertices with H, and then F should be a supergraph of H in an edge inclusion-wise sense. Okay? And then we're going to compute a flow cut relaxation value, which I'll denote as LP F of G for every possible F, and then output the minimum value. Okay? So that is my algorithm. And then at first, it looks kind of bizarre, and then it's not clear whether there's a relaxation or not. So let's try to see. Okay, so this is an algorithm. So one thing you can easily establish is that for every F, since F is a supergraph of H, so we know that LP HG is at most LP F of G. That's true. And I claim that there exists F among the graph we considered, such that LP FG is at most opt HG. Okay, so let's try to say this. Okay, suppose, look at this example. Okay, so we have H and we have G, and then suppose that we have some optimal solution. Okay, so delete this optimal solution from the graph. Okay, so after deleting this optimal solution, we can see that all the cut requirements given by H are met. But if you look at the supply graph after deleting opt, then we can see that actually we deleted much more than we needed. Okay, so actually in this example, S1, S2 are completely separated, and then T1 and T2 do not have any outgoing edges at all. So if you construct another demand graph F with the same set of vertices, such that I'm going to put an edge from U to V if there's no path from U to V here, then the resulting F in this case will be complete bidirected graph. Okay. So this is only for this example, but you can easily convince yourself that for any H, for any G, and for any optimal solution, actually for any feasible solution, the resulting F constructed in this way will be always unambiguous. Okay, that's obvious because if you cut U to V, then you must cut U to W or W to V. So this proves that there exists F that we considered, where opt FG is equal to opt HG. So, and then we just proved that there is a F such that LP FG is at most opt HG. So if we combine these two facts, then we know that the value output by our algorithm, which I'll denote as alg HG, is a sandwich between opt and LP. Okay? So it's going to be always a relaxation, and then for any instance, it's going to do as good as the LP. Okay, so I stated this algorithm as an estimation algorithm, but if you really want, you can these can be captured as a single LP by running a flow cut LP for every possible F by blowing factor of a 2 to the k square. Okay. So but I didn't present the LP, so what does a gap of this algorithm mean? Okay. For fixed H. So I'm going to claim that the gap means an ambiguous F and G such that LP FG is less than opt HG. Again, it looks kind of bizarre because we are comparing apple and orange. But at least I show that there is some F that LP values are less than opt. So I'm not asking you to do the impossible thing. And then actually, it's true that I'm asking you to present me a stronger gap instance. And then the theorem is actually says that for every fixed H, a gap of this algorithm implies a matching unique image hardness. The proof is essentially the same, and then I just resolve this issue of the bypassing. So I think this algorithm is also very natural, but it's gonna become more natural if we consider undirected analog. Okay. So by the way, so running time of this algorithm is 2 to the k squared times n to the constants. So it can be called as FPT approximation algorithm. So if you look at the undirected analog, then unambiguous F means a complete p-partite graph for like some p, which means that complement is just like disjoint clicks, union of disjoint clicks. So if you look at the algorithm is just like essentially guessing which terminals belong together in the optimal solution, and then run multi-way cut algorithm. And then we saw on Monday that for any instance of multi-way cut algorithm, we are going to get 1.3 approximation. So for every h, multicut h in undirected multicut h can be approximated within a factor of 1.3 if we allow time k to the k times n to the constant. Okay, this is really good. But again, if you really care about the optimal approximation ratio for the fixed h, then you can try to find a gap instance, which is an unambiguous F and G such that the earth mover LP, the LP for the multi-way cut, is less than opt of H and G. Okay. And then, but we already know that earth mover LP is proved to be optimal for multi-way cut. So I haven't verified this, but it's very conceivable that their proof already proves that this algorithm is the best estimation algorithm for undirected multicut H, if you really care about the approximation factor between 1 and 1.3. Okay, so this is all I wanted to say about multicut. And so as I promised, I'm going to say something about the global cut problems. Okay? So let's consider the ST bicut, which is not global convergent. So ST bicut is a special case of a multicut H when H is a bidirected edge between S and T. Okay, so the problem is given G and S and T, so we are given terminals. We want to remove the minimum arc such that there's no ST path and TS path. Okay. So the global bicut, as you defined, is a problem where given a graph G, we want to minimum number of arcs such that there exist two vertices where there's no ST path and TS path. Okay? So we can choose where to put terminals to minimize the cut value. Okay, so this relationship is very similar to relationship between three-way cut and three-cut. Okay. So three-way cut is we have a graph G and STU in undirected graph, and then we want to remove the minimum edges such that they are separated. And then three-cut, one way to view this problem is that given a graph G, we want to remove the minimum edges such that there exist three vertices that are separated. Okay. And then we know that this problem is NPR, and this problem is NP. So, and then we observe the similar phenomenon here as well, even though in the approximation sense. So ST bicut, by earlier work, we know that it is unique games hard to approximate within a factor of 2. But in this later work, we proved that global bicut has something slightly better than 2 approximation. So there's like some non-trivial distinction here. So this was for the global cuts. And then in the earlier paper, I also proved the first super constant hardness for various cut problems called length-bounded cut, shortest path injection, and firefighter. So they're all based on the single framework that I named as a length-controlled dictator test. So it is just taking some LP gap instances to unique games houses in a very similar manner that I just showed you earlier. And so one personal open question is that can we improve hardness over more cut problems that were open? And actually, so what I really wanted is that I wanted a general theorem that unifies the current results. So far, I just had to look at every problem individually and then see their LP gap instance and then see whether my proof works there or not. But I really wanted a general theorem that unifies many problems. But I was stuck, and the main reason is that I don't know how to formally unify various cut problems. I think so these type of the optimality results were known for max CSP. And then CSP is a very general, it's a very good framework that unifies many problems. But for cut problems, I didn't know how to do it. So yeah, that's one personal goal. So and then I have many other open problems in this direction. So actually, the immediate open problem is to see whether flow cut LP will be optimal for the directed multicut H. Okay, it's going to have a practical impact because that's going to save us 2 to the k squared time. Okay. So. And then the answer can be negative in a sense that we have an instance, G and H, such that LP HG is strictly less than alg HG. So there, if you fix both supply graph and demand graph, then there's an example where LP does strictly worse than this. But we are interested in the worst possible gap for fixed H. So it's still possible that for every H, if you fix H, and then take the maximum gap, then they may be the same. So it's like very immediate open problem. And then another open problem is to find the interesting H where we can do much better than this trivial approximation. So we know this for multi-cut and linear K-cut. And then as I said, they all use a flow cut LP. So maybe you can do much better for some other H using the new LP. And then the final open question is to find the optimal rounding algorithm. So I just stated it as an estimation algorithm, or LP, but I don't know how to round it. And then this problem also exists in the earlier work of MNRS or EVW, where they show that certain LP is optimal for undirected multi-way cut or mean CSP. Okay? So somehow max CSP, we know that some SDP is optimal, and then we know rounded, at least theoretically. But for these problems, these rounding algorithms are missing, so that's going to be a very good research direction to study. Thank you.
Questions for anyone? It's been a long day, so thank you all the speakers.